I misunderstood on the board meeting the other day, and it was on the 28th, which it's not, which was kind of exciting for me because 28th is my birthday. So I thought, cool, I get to go to a meeting on my birthday, but not to be. But anyway, next meeting is February 22nd. It'll be right here at the same time. Also notice that the public nights are kind of rolling back into view again. Public nights, for those of you maybe newer members, are nights when the Farpoint Observatory is open to the public. We rely on volunteers for those kinds of things, so if you would want to come out and volunteer for that, we would certainly appreciate it. Don't feel like you have to be proficient in running a telescope or proficient in finding your way around the sky, although if you are, we certainly would welcome that expertise. There's plenty to do for everyone, and we really strongly encourage people to. It's also, what I've found is a really good way to learn. When I first joined NECA, which hasn't been that long actually, my understanding of the night sky was pretty spotty, to be honest with you. And I've learned a lot just by kind of over listening in on the sky presentation that Jan typically does when we're out there. So a good way to kind of learn a little bit more, a good way to kind of mingle with members of the club, members of the general public, and so on. So, anybody else want to say anything about public nights? And then next general meeting is March the 28th, and so on. Starting to head into spring. Any other announcements? Anybody got anything they want to talk about?
Is there any topics people want on a presentation?
Yeah, that's something I always kind of ask about at the end, but might as well ask about it now. Is there anything, tonight's topic came out of a conversation at the holiday party in December, so we kind of are going to talk about magnitudes, which turns out to be, at least to me, a really interesting thing to talk about. But yes, if you have an idea, if there's something you want to hear about, if there's something you want to talk about, I would encourage that. I don't consider this seat up here to be mine by any means, and in fact, I'd rather encourage people to come. And Dave, you said you might do something on telescopes next.
We had a member ask. They're interested in buying a telescope, and they just want to learn some of the fundamental things about the different kinds of telescopes and what each one is really good at doing. So that'll be a topic. Is anybody else interested in that topic?
Yeah,
absolutely.
Okay. And it's often a good idea to start slow, in case anybody's wanting to go out and buy something right now. But it's really good to get involved with our club, so you can even look through other people's telescopes that are in the club, or even some of the club's telescopes to see. And maybe you don't want to buy your own because you have access to what Farpoint or our observatory could provide for you. So yes, sounds good. We'll gear that one up. And I learned real early, you don't need to buy new, because a lot of people bought telescopes and now they're coat hangers and clothes racks and stuff. So there are gobs of used equipment out there.
Dust collectors.
So anyway, those are my quick thoughts on that topic.
Yeah,
we'll do a presentation.
The other thing I found, and I would agree completely, that if you can find something that's used and still in good shape, telescopes are a little bit like cars. As soon as you buy one and drive it off the lot, its value goes down pretty remarkably. So you can get in some cases, telescopes that are 2 or 3 years old for maybe half of what you might pay for it new. So kind of a good thing to know. So anyway, so we'll plan on talking about that next month then. Any other announcements? No?
I will point out that March, let's talk about open houses. March, actually the 16th is our first open house.
Yeah. So, yes, we're headed back into the warmer time of the year when we can expect people to show up.
And for our members, we have member nights this year too selected, but we don't advertise those on our website. So go to your group's IO calendar to see the dates for those, because those are just for members, and we don't want the public out there when we say it's a members night.
And did we get through the cold spell okay with all the equipment and things? I know there
No,
was.
the equipment won't be hurt by it.
Okay.
I actually was able to roll the roof off a couple of nights after all the big snow and when the temperature was -10, so.
Wow.
Roof rolled off okay and rolled back on, which was more important to me at that time.
Yeah, I always kind of wonder about the lubricants and stuff when it gets super cold. And
Actually, there's not much in the way of anything that's gonna freeze up on that.
Got your tongue?
On that supply, and the telescopes, there really isn't any
Okay.
no.
lubricants to worry about,
Can you
anything
grab that
that's gonna
clipboard
thicken up
and-
or, you know.
Yeah. I know that was something when I was working with telescopes in college, that was something they worried about, so
Yeah.
maybe the technology has improved in the last.
Well, I think it's, yeah, and whatever lubrication is needed is usually closed in, so it's not affected very much. And it's-
Wets, right?
It's usually, the greases and lubricants now available.
Yeah, I'll let you write your name. I'm bad at names.
You know,
And
so
then
those
you-
are
yeah,
minus
too.
50,
You can
so-
do family and then
Okay.
fold it up in there, that way I won't lose.
All right, any other club business? All right, well, a couple of things that kind of caught my eye. You know, I've kind of gone back and forth on going through the news. You know, I went through a period of finding articles where they compared asteroids to things. I saw one the other day that was they compared it to one that's about to pass or maybe pass today to 5 giraffes. You know, so, but I figured I kind of played that joke out, right? You just squeezed all the humor we could possibly can out of that one. But there was a couple things. This is one I thought was kind of interesting because this was something that was only discovered, like day before yesterday or something like that?
Yeah.
And it entered the atmosphere maybe yesterday?
Thank you.
Was it that?
I think it was the day before, but maybe, what did it yesterday, I mentioned last night. It was seen over Europe, so it was, you know, our daytime.
Yeah, and I've kind of seen conflicting things on it, but there was I follow a Reddit site that's meteorite observations, and it was observed to break up over Germany, and they think they're strewn in kind of near Berlin, basically.
Just north of Berlin, wasn't it, I think?
Right, and they actually even had a little map out there. Apparently they have some kind of,
People are out looking for,
so people are out looking for stuff, yeah. So apparently it broke up in the atmosphere, and
Some were found, actually.
pieces of it that people have been found.
Yeah.
Yeah, when I was this past holiday, we went to Santa Fe, my wife and I and the kids, and I went into a rock shop there, you know, which I don't know if you've ever been to Santa Fe.
Oh, yeah.
It's a cool place, but it's also a little pricey. It's like, you know, the Aspen of New Mexico. But anyway, I went in this rock shop, and the guy had a meteorite section, and we got to talking, and I asked him, oh, and he had like pieces of stuff that were unbelievably expensive by my standards. I asked him, you have any pieces of the Brenham? You know, the Brenham meteorite was a palisite that landed in western Kansas sometime, I don't know, prehistorically, I think, but pieces of it have been recovered. Anyway, you have a piece of it, right?
Yes, I have a couple of pieces.
So he showed me this beautifully polished piece of this thing about this big around
Oh, yeah,
$11,000.
Yeah.
And I was like, yeah.
My pieces aren't quite that big.
Yeah, this was beautiful though. It had been, you know, beautifully polished. But apparently this guy, as a sideline, kind of teaches classes in how to find meteorite. I'm thinking about it, you know. I'm giving it some thought of signing up for one of these. But anyway, this was one that kind of caught my
And you
eye.
can buy a lottery ticket at the same time.
Yeah. You know, maybe I'll get lucky. Maybe not. Anyway, this was one that I kind of, given the club interest, I thought was kind of, I like the way they show all these rocks here, you know. This was one I thought was also in some ways a little relevant to us in a very, very, very indirect sort of way. This is the Vera Rubin telescope, which I don't think is actually operating yet. It's built and, you know, being tested and all, but it's in Hawaii, I believe, on whatever that mountain that all the other telescopes are on. And it's named after Vera Rubin, who was a very famous astronomer. That she basically made the discovery that would suggest that there's dark matter. You know, she measured how fast galaxies rotate and found out they don't rotate how fast they should rotate unless there's something mass out there we can't see. But anyway, so this telescope is named in her. I believe she's probably passed away now. But anyway, what's kind of cool about this telescope is that it, you know, most of these really huge telescopes are kind of command driven, I guess you could say. The astronomers apply for time, and then they say, okay, you've got, you know, 2 nights, and then you tell them where to point it, right? This one is a surveyor, and it's a fairly wide field, so it's just going to, you know, do the whole sky and then do the whole sky, and it can do the whole sky very rapidly, like in a couple of nights. So this is going to be like repeated coverage, which is kind of cool because, you know, one of the things that gets lost in static observation is that it's static, and you miss dynamism, right? You miss change and things like that, and, you know, moving objects and all that. And this probably has the resolution to detect some of the types of things that, you know, like the asteroid surveys and stuff we're looking at. So this could turn out to be an extremely rich data source for looking at solar system objects and lots of other stuff as well. So I thought this was pretty interesting. And the data is, a lot of the funding for this came from the U.S. National Science Foundation, and the National Science Foundation requires that any data collected from their funding is in the public domain. It has to be freely accessible.
But isn't there a time frame?
There's a time frame, yeah. The principal investigators of the projects get the first crack.
Sure.
So I don't know. Was there a number now? It used to be like you had to release it in a year or something.
A year
like
is
that.
what I used to hear.
Yeah, I know when projects I've been on that were funded by NSF, we had to make the data publicly available with a year after, you know. So anyway,
Is it multiple mirrors or lenses? I mean,
I think it's one really big mirror, but it's a really, really fast mirror, so it's a short little stubby tube. I've never actually seen
It's
the
like an
telescope itself.
f.8 or something.
Yeah, very
It's-
fast, very
it's
wide
extremely
field.
fast.
Yeah, very wide field. So it's, you know, it's doing the whole sky like every 2 nights, you know. And this place where it is in Hawaii is very high altitude, very clear skies. So it's so high altitude that it's almost higher than people can really practically work. You know, people that go up there to work at these, I've talked to this one guy who worked up there, and he said, yeah, you know, I write instructions out for what I'm going to do, and I try to write them as if I was trying to explain it to a 6-year-old. Because by the time I'm up there at 14,700 feet, there's no oxygen, so I'm going to be reduced to thinking like a 6-year-old, you
It's
know.
just fog. It's
Yeah.
nothing to do.
You know, and they take oxygen bottles, and this you don't even have to. It just runs pretty much automated. So anyway, so I thought this was kind of an interesting thing. This is from Universe Today, so if you want to,
Yeah,
Indulge
basically going to put us out of business, so.
you think so? I don't think
Our
so.
follow-up is going to be a little.
But this is going to be
impacted
this is going to be
considerably.
discovery stuff. And you know, the people
Well,
still have to
but
do
you're
the
going
work.
to do follow-up the second night.
Yeah, I still think there'll be a role. You
And
know?
it'll probably be a role for fast movers.
Yeah.
Close by, very, very close ones, like the one that hit just the other day.
Yeah. Well, we'll just have to go to measuring
Yeah,
rotation rates,
photometry or radar.
rotation rates or something
Yeah.
like that. Speaking of motion, this is a much larger scale. And this was one I thought was just sort of interesting because of the chain of inference that was involved in this. So basically what they were claiming here is that, you know, big galaxies often have little galaxies around them, little satellite. The Milky Way has several of them, like the Magellanic Clouds. If you ever go to the southern hemisphere, you can see the Magellanic Clouds. And they all kind of orbit around it. And what they were claiming in this paper, and I unfortunately don't have the technical knowledge to really assess this claim, but they were saying that some of the satellite galaxies that we're seeing go the opposite direction, right? Some of them go one way, some of them go the other. Eventually, if given enough time, they will all settle into a really similar orbit, just by the way gravity works. And so the fact that they were still more than they would expect going the wrong way kind of suggests that maybe they haven't been there as long as we thought they were, which means that maybe the universe is not as old as it's thought to have been. Again, I don't really have any basis for critiquing that idea, but I thought it was kind of interesting because, when I was a kid, the universe was 18 billion years old, then it was 15, and now it's like 13 and a half. And, this is a different way of kind of refining that, but I thought that was kind of interesting. So, again, this one was from, I think, Universe Today as well. So, this is one, too bad Justin's not here, black hole news. The oldest black hole ever seen. It's thought that this probably formed somewhere in about 400 million years after the Big Bang, which, 400 million years is a really long time, but on the scale of the universe, it's nothing. It's a kind of a flash. And what was interesting to me about this one was that, at least the way I always kind of understood it, you had to have big stars collapse in order to get a black hole. So stars probably came along after about 100 million years, right? So that left 300 million years for stars to go old, die, and collapse, which I suppose it was a big enough star. Okay. Or it means that there may be other ways that these form. So this could imply a kind of a different formation route.
Kind of superlunar, right?
Yeah. So anyway, that was I thought that was kind of an interesting article too. And these all came from the same edition of Universe Today. I didn't get too far in my reading. I got stuck on these. So. And finally, one that I just thought I'd throw out there, speaking of black holes, we've talked about kind of citizen science and things, the way that people can make a contribution. Here's a new one. This one is the Black Hole Hunters. They had a citizen science project that has now kind of wound down of looking for exoplanets in the TESS data set. This is looking for black holes. So if you want to participate in this, you can sign up. You don't need any telescopes or any of that kind of stuff. In fact, if I go to their website here, you can kind of see this. They train you in how to recognize light curves from the TESS data set that would be suspected black holes. And this is the sort of thing that machine learning does not work especially well for, but human brains do. So this is, kind of a brilliant idea on the part of these, investigators. It's like, we'll get a bunch of volunteers to do this. And last time I checked, they had something like over 7,000 people volunteering to do this. So if you want to, they're 14% complete already. So, you might want to get in on the action now. But if you want to do some kind of citizen science stuff and you don't have a telescope or you don't have the patience for that sort of thing, or if it's too cold out there, this is a good way to make a contribution. Okay, so those are just a few things I thought I'd kind of throw out there. All right, so we often, as we know, kind of talk about a constellation for a little while, and it's kind of exciting for me because the skies we're heading into now are kind of my favorite skies, right? The Christmas skies and the early winter skies, I think, are the richest and coolest looking ones. My childhood experiences of laying on the rock in our backyard and looking up at the skies, the December ones were always the best. So I was really looking forward to this and thinking, I need to pick a good constellation. And I got to thinking about it, and I thought, it would be tempting to go with like one of the big flashing ones like Orion or something, but some of them get overlooked. And so I decided to go with an overlooked one this time. So I'm going to go with Canis Major. There's another reason why I picked this one, which we'll get to as we go along here. But I thought I would talk about this one because in some ways it's kind of interesting. So it's part of that cool Christmas sky, right? All the really bright stars and bright objects and interesting looking ones. And there's Canis Major right there. So this particular view would be what you would see tonight at 9:16:23 local time. So this is if the sky were at least a little bit transparent, you might possibly see it as it's not. Anyway, so let's take a little bit of a closer look at Canis Major. So first of all, how to find it? It's pretty easy, actually. Made exceptionally easy by the fact that it has a really bright star in it, which is one of the other reasons why I chose to talk about it. But if you want to find it, just find Orion's belt, and it points right at that really bright star. Sirius, and then you can kind of reconstruct Canis Major from that. It has, I believe, 7 named stars in it. There's, of course, some that are just numbered. I think it has 7 named ones in it. It also is one of those constellations that kind of sort of maybe looks a little bit like what it's supposed to be. I mean, I think if somebody asked me to draw a dog, this is what it would kind of look like. So, I can kind of relate to that, which makes it a big contrast to Canis Minor, the small dog. Canis Major, by the way, means the big dog, right? Canis Minor, the small dog, which to me just looks like a line.
It's pretty small.
And yeah, it's a really small dog. And by the way, Canis Minor is going to enter into our story here a little bit too, so we're not going to ignore the small dog while we talk about the big dog. But anyway, this is how it would look. This is actually would be a little later in the year than what we are right now, but this is a kind of view that you'd see. So pretty easy to spot.
I want to jump in there real quick. I want to go back to that one. When I deal with people, and I'm always telling these stories and everything. Sirius is the large dog. He's the hunting dog, and he's following Orion Hunter. Procyon, I say he's in Canis Minor. He's the puppy. I call that the puppy star, like people remember. And he's, of course, running off the other direction. And then on the slide before, if you look at that image, you'll look that right underneath there is a rabbit.
Yeah,
He was the rabbit. So you've got a hunter, a hunting dog, and a rabbit who's just sitting there laughing at him because they're paying no attention whatsoever. And the puppy isn't paying a whole lot of attention to it. So that's just one of the things it's one of those mnemonics that helps with people. So the great hunter ain't so great.
I wasn't sure if there would be much mythology associated with with Canis Major, other than it's Orion's hunting dog. It turns out there is, and it's kind of an interesting story. So the myth involves a dog named Laelaps. And Laelaps was a special hunting dog that never failed to catch its prey. And I had to write a few names down here just to remind myself. Well, so Laelaps, the dog, was actually given to, with the myth, as we've seen all along, there's always bad behavior involved, right? The gods, the heroes, they were awful, awful individuals. And, not much of an exception here. But Laelaps actually belonged to a woman named Procrus, who was the daughter of King Minos. And she married a Greek hero, Cephalus. Cephalus, unfortunately, came into the sights of Eos, the goddess of love. And Eos decided that she was going to kidnap Cephalus and keep him as a, keep him. And and so that went on for several years, but he pined away for Procrus. He really was in love with her and wanted badly to get back with her. Eos would work on his mind and tell her, oh, she's off, fooling around, you don't want her. Eventually, though, he went back to her. In order to, allay his suspicions, he disguised himself as someone else, and unfortunately, Procrus fell for it. So that made, complicated the situation a little bit. So they were kind of on the outs for a while because of that, which seems like kind of a dirty trick, but these were Greek gods, so kind of expect that, right? Eventually, though, they had a reconciliation, and at one point, Cephalus actually cured. Dang it! Now I'm forgetting. Zeus. He had a really unusual medical condition that, since we're a family club, I'm not going to go into any detail on. But he it really was pretty bad. Anyway, Cephalus cured him of this condition. And in gratitude, he awarded her 2 presents. He gave her a spear, that javelin that never missed, and a dog, Laelaps, that never failed to catch its prey. Unfortunately, the story did not end particularly well. Laelaps' husband, Procrus, was hunting with Artemis, who's a goddess of the hunt, right? And he had taken this javelin with him, because I don't know, to me it seems like, I'm not a hunter, so I can't really comment on this, but it seems to me like if you got a javelin that never misses and a dog that never fails, it takes a lot of fun out of it, right? You know, it's like having a gun that won't miss. After a while, there's no challenge, right? Anyway, he had taken this spear and was out hunting, and was actually hunting a monster, right? This wasn't just hunting for the fun of it. They were hunting a monster. Unfortunately, Cephalus came upon him. He mistook her for prey, threw the javelin, and killed her. So this is the part of the painting here. This is actually part of a larger painting called Procris's Death, painted about 1500, and that's Procris right there, or sorry, that's Laelips right there, the dog kind of mourning his lost owner. Anyway, the other part of this, though, I think the more interesting part was the Laelips and the Tumessian fox. Right, so Laelips was a dog that never failed to catch its prey. The Tumessian fox was a fox that never failed to escape from its hunters. And so when these two got together, it became this endless round of chase and chase and chase and chase, to the point where Zeus finally realized that there was going to be this was never going to end, right? And so his solution to the problem was, first of all, to turn them both into stone. So he turned Laelips and the Tumessian fox into stone, and then place them in the sky. So they got placed in the sky as Canis Major, the dog, Laelips, and Canis Minor, which is now referred to as a small dog, but it also is a representation of the Tumessian fox. So that's the little bit of the mythology behind it. They're also, as Jen pointed out, closely associated with Orion the hunter, which I'm not really sure what the mythological story behind Orion is, but maybe that's something we can kind of address at another time. But anyway, so this is the two sort of former adversaries placed in the sky. And again, they're kind of, as Jan pointed out, they're also pretty closely associated with Orion the hunter. They're hunting the rabbit, which apparently they've never caught. So kind of makes you wonder if Laelips is really living up to his billing, all right, if he can catch this. Anyway, so that's a little bit of the kind of mythological story behind Canis Major, which I expected to be a little bit dull, to be honest with you, and it turned out to be kind of interesting. But one of the reasons why I wanted to talk about Canis Major a little bit is that it kind of segues into the other thing I want to talk about tonight, which is stellar magnitudes. So we'll make that connection here as we go along. But stuff you might see, oh, here's another thing I thought was interesting. There's actually a wine called Laelips. Laelips is actually the vineyard. It's not the wine type, it's the vineyard. So here's their Cabernet Sauvignon, which I don't know a whole lot about wines, but I'm pretty sure that's a red wine. And you can see on the label, this is a 2015, which I have no idea whether that was a good year or not, but you can see that it has the representation from a star atlas of Canis Major kind of reared back like it's often depicted. I thought that was interesting, you know. If I were a wine person and this was not grossly expensive, I'd buy a bottle just for the label. I thought this was even weirder. That's a harmonica. So apparently there's a harmonica brand that's Laelips, which I don't know. I don't play the harmonica. I don't know anything about harmonicas. I don't know why a harmonica would be associated with a dog, but anyway. So that was another little thing that was named after Laelips. Okay, so as far as stuff that's actually in Laelips then, or that's in Canis Major, it's a relatively small constellation and not that large a number of stars, particularly named stars, but there's some pretty interesting stuff in it. There are a few deep sky objects, but I actually think the stars in it are the more interesting part of it. So there are some deep sky objects, some clusters. There's the little beehive in 41. Although Carolyn, I believe, was Carolyn Herschel that is named after this, and that actually is a little preview of next week, because I'm thinking, or next month, because I'm thinking next month I'm doing a presentation on Carolyn Herschel and Carolyn Shoemaker, because they're both named Carolyn and they both discovered a lot of comets and they both had interesting lives. So I'm thinking about doing that for next month's presentation. If you got other ideas, I'm more than happy to hear it, but I've been kind of putting together notes on that one. I'm going to call it Carolyn and Carolyn. Anyway, but I believe Carolyn Herschel discovered this particular cluster. So there are a couple of deep sky objects. Here's one I thought was pretty interesting. There's this thing in it called in Canis Major called the Canis Major overdensity, which is not a very, not a very poetic name, to say the least. And there's been a pretty healthy debate about whether it's a galaxy or not. And what I've been able to see lately refers to it pretty frequently as the Canis Major galaxy, which maybe suggests that it is. And if it is, it's the closest galaxy to the Milky Way. So here's kind of a representation. There's the Milky Way right there. The sun's about right here. The Canis Major galaxy, if it is in fact a galaxy, is actually part of this long stream of material that's kind of wrapped around the Milky Way. And it's thought that that's material that came off the galaxy as it traveled through space. So it's called an overdensity because there's more stars there than you would normally expect. And it could actually be a galaxy. And if so, it's a relatively small one and the closest one.
Closer than Andromeda?
Oh yeah, way closer than Andromeda. Well, there's a bunch of galaxies closer to Andromeda, like the Magellanic Clouds are closer. These are satellite galaxies. They actually orbit around the Milky Way. So anyway, I thought that was a little bit of an interesting. I thought this stream of material coming off of it was, can you imagine something the size of a galaxy that's just leaving stuff behind as it goes? It just is a interesting thought. So anyway. So that's it could be the closest dwarf galaxy to Earth. And finally, of course, I think the stars are what make Canis Major the most interesting thing. And one star in particular, Alpha Canis Major, which of course is called Sirius, the dog star, right? Sirius is like a lot of star names derives from Arabic. Greek, sorry, yes. And it means the scorcher, or the scorching one, or something like that. And it's thought that, it's thought that it got that name in antiquity because it was associated with summer, the arrival of summer. But, it's thought that this bright star, had kind of heated up the ground. But anyway, what's interesting about it, among other things, is that as stars go, it's not a particularly large one, or a particularly hot one. It's a little bit bigger and a little bit hotter than the sun. But its magnitude is minus 1.33, and it's the brightest star, not the sun, in the sky. And actually, that's one of the reasons why I picked this, because the next thing I want to talk about is the magnitude scale. So this kind of gives a nice, in my mind, segue to talking about magnitudes, because the first question that would come to my mind if I was new to the magnitude system and somebody said the brightest star in the sky has a magnitude of minus 1.13, I'd say, what kind of scale are we talking about here? And that's what we're going to answer for the rest of the night. But anyway, that's Canis Major is actually a double star. That's its companion right there, which is much smaller but actually hotter. It's a star that's a hotter spectral type. Anyway, so that's Canis Major. The other star I thought was pretty cool was one you actually can't see. Oh, and by the way, Sirius is part of two asterisms. It's part of the triangle right there, and it's also part of what's called the winter circle sometimes. So there's the winter triangle right there. There's the winter circle, which looks like a circle that I would draw because I'm not very good at drawing. Sometimes it's called the winter hexagon, which is a little bit more generous because it is closer to being a hexagon than it is to being a circle, but it's not really close to either one. But it is, I think, kind of a good way to kind of keep track of the stars. So Sirius, Rigel, which is the left foot of Betelgeuse, Aldebaran, Capella, Pollux, which is one of the twin heads in Gemini, and Procyon, which is the puppy star, right? So that's an asterism that you can use to
I
kind
have
of.
also heard it called the football.
Oh yeah.
This country, yeah.
Yeah, I can see where it's a little football-like.
Yeah. I think they had too much libation.
Yeah. Well, it doesn't really look like any of those things to me, but it is kind of a common asterism, and one that I use it to keep track of where I am. So perhaps you can do the same. There was one other star I wanted to talk about in Canis Major because it's I believe, either the largest or second largest star that we know about. For the longest time, it was the largest star. This one's VY Canis Majoris, and if you know a little bit about how star names are made, VY tells you that it's a pretty dim one. This is far too dim to actually see with the unaided eye. And yet, it's this absolutely huge star. So here's a little bit of its kind of statistics. Notice its apparent magnitude. It's a variable star, somewhere between 6.5 and 9.6. 6.5 would be borderline visible to the naked eye if you were in a really dark place and you had really good eyes. 9.6 is not off. You can't see something like that. But here it is, right there. It's kind of right, and it's a almost unnoticeable star in its constellation, right? And yet, if you could see it up close, it would look something like that. That's a pretty scary looking thing. But this is one of the stars. You know, there are red giants and red supergiants. This is a red hypergiant star. And if it were in our solar system, centered on the sun, that's how big it would be. Right? It would extend out past the orbit of Jupiter, not quite to the orbit of Saturn, but you know, that thing's a monster. Earth would be about like right there, right? So this thing is just a monstrous star. For the longest time, it was the largest star we knew about. Now I think it's second. I'm not sure which one took its place, but I thought it was kind of an interesting contrast, right, between Sirius, which is a really bright star, but not very, intrinsically bright, right, and this thing, which is a very dim star, but huge and, much more luminous. So anyway, that I thought that was kind of an interesting contrast. And that actually kind of brings me to the thing that I wanted to spend a little bit of time talking about tonight, that somewhat mysterious, from time to time, magnitude system. So again, this came from a comment at the Christmas party, and it was one of those things I always thought about, magnitude, I know all about that, right? And then I got into looking at it and realized, I don't, there's a lot of stuff here I had no idea about. So we'll talk about magnitude. And of course, one of the first things you ever notice when you look up at the sky is that the stars are really not the same, right? They're different colors, they're different sizes, they're different brightnesses. And so that's sort of a fundamental observation that you can make about them, right? Why that is a little bit beyond the scope of what we want to talk about tonight. But what I do want to talk about is kind of how it came to be that we have a system for describing the brightness of these, and why that system, in some ways, doesn't make a whole lot of sense, at least not a whole lot of what I would consider straightforward logical sense. Anyway, so as things often do, the story starts in antiquity, and it starts with Hipparchus. Hipparchus was probably the most distinguished astronomer of the ancient world, was a polymath, actually did quite a lot of science work, but was considered one of the founders of astronomy. You see this representation of him. That is conjecture. Nobody has any real idea what Hipparchus, looked like, because there was no contemporary art of him. So we really have no idea what he actually looked like. So you see this representation of him quite a lot, and I don't know, perhaps it's accurate, maybe it's not. It is known that he was born about 1900 BC, 1900 before the Common Era, in Nicaea, right, which is now in Turkey. Worked mostly in Rhodes, which is an island in the Mediterranean, and in Egypt. And one of the things that he did was compiled catalogs of stars. He was really interested in where they were, right? The position. He was probably, you could think of him as one of the pioneering astrometrists too, measuring the position of stars. He was actually the one that created the stellar coordinate system, or created a stellar coordinate system, which is similar in a lot of ways to the one that we use now. But his catalog, he also wanted to describe the brightness of what he was seeing, right? He was cataloging these things. And so he wanted to, he needed to create a magnitude system. So the magnitude system that is used was essentially created by Hipparchus. It was actually popularized more by Ptolemy, because it appeared in one of Ptolemy's star catalogs as well. And Hipparchus's star catalog doesn't survive. There's no copies of it now, but Ptolemy's there is. And so it's thought that there was probably some relationships between them. They were kind of similar. But this was what Hipparchus was doing. He used a device which I can't remember what it was called, but basically it looked like a telescope. Doesn't have any optics and it was a tube, right? But he used that to measure the position of objects in the sky, and then he used his magnitude system to describe their brightness. So Hipparchus's magnitude system kind of worked like this. Basically what Hipparchus did is he took the 20 brightest stars in the sky and he designated those as stars of the first magnitude. Here's where the confusion kind of starts a little bit about the system though. Why is it that bigger numbers mean dimmer objects? He was using magnitude here to mean something more like size. And we rank things in size intuitively by, first magnitude is biggest, right? And so on. And so it's thought that that's probably what Hipparchus was thinking on this. He wasn't necessarily thinking strictly in terms of brightness, but in magnitude and size. So he took the first 20 brightest stars in the sky and he called those stars of the first magnitude. And then he took the next 20 and called them stars of the second magnitude. And he kept dividing these up. So this was a categorical measuring system. And that's one of the other things that has evolved over the years. It's gone from being a categorical system to being more of an ordinal system, right? One where the numbers actually have physical meaning. But in the beginning, it really didn't. And then finally, he got to the dimmest stars that he could see, and he called those stars of the sixth magnitude. So this is, to this day, why we think of sixth magnitude as the cutoff for what can be seen with visible light with the naked eye. That's because that's the way Hipparchus designed the system. And he, again, meant magnitude to mean big and not necessarily bright. But unfortunately, or fortunately, or whatever, when Ptolemy got a hold of the system, he was much more interested in brightness. So he took Hipparchus' system, but he began thinking about it in terms of brightness. So this is a page of Ptolemy's star catalog, which was a little more extensive than Hipparchus is thought to be. Again, Hipparchus doesn't survive, right? There's no copies, extant copies of. There's, I think, one page or something like that somewhere. But anyway, you can kind of see the longitude and latitude, right? Those are the stellar coordinates. We think of them as right ascension and declination now, but it's basically the same idea. And then there's the magnitude, magno, over here. And you notice there are numbers like 3s and 6s and 4s and 2s and all these things that followed from Hipparchus' system. So this is where the system came from. Of course, like anything else, it had problems associated with it. Maybe it's not fair to refer to all these as problems, but I'm going to anyway. One of the problems for me as a person who measures things is it's qualitative, right? Magnitude values aren't defined in terms of any physical quantities. They were just size. Well, I guess you could say size, but they were categorical, right? So 2 wasn't necessarily, 2 had a relationship to 1, but that came along later, okay? In the original development of the system, there were just labels for categories. It had a fixed high end, and it was imposed by limitations in human vision, right? Partially it was arbitrary, but partially it was imposed, right? So Hipparchus said, and Ptolemy said, 6 magnitude is the brightest that we can see. It assumes that all the stars are intrinsically the same brightness and are all equally far away, which is not necessarily an explicit assumption, but when you start digging into the system a little bit, it kind of assumes that. And that's probably consistent with the way they thought about the sky back then, right? The idea of it being three-dimensional and distance scales and all that sort of thing hadn't quite come about yet. That came several hundred years later, actually. So it made that assumption about it. It's also based on visual observation, which means it's subjected to the limitations of human color vision, which we'll talk a little bit more about later. But human eye is not equally sensitive to all colors, and stars are different colors, right? So something could be different brightness to the eye than it might be to something that measures a little bit less biased. And finally, it's backwards, right? Brightest things are 1, and the dimmest things are 6, and that just seems a little backwards, right? So these were all problems, and yet the system has kind of stayed in use in a highly, highly modified form ever since, largely because it got associated with all these catalogs, right? It got kind of grandfathered in a lot of ways. So the system persisted for quite a long period of time, but it started to undergo some changes. One of the people that was instrumental in those was a very famous Italian scientist, Galileo, right? Galileo, among other things, of course, anybody that's ever taken a physics class, Galileo, right? Rolled balls down ramps and stuff like that to figure out how things move. But he was also really interested in astronomy. And he was one of the first people to ever use a telescope. He didn't invent the telescope, that's a misunderstanding. But he was one of the first people, probably the first person ever to use one for astronomy. And what he found was that when you look through the glass, when you look through the telescope, there's a nice quote from his Sidereus Nuncius, which I have no idea what that means, but he wrote it in 1610. He said, there's crowds of stars below the 6th magnitude. The largest of these we designate as the 7th magnitude. So there's that system starting to slip a little bit, right? Now we've got 7th magnitude stars, and they are even dimmer than 6th, and they can't be seen with the naked eye. And that, of course, kind of opened the floodgates a little bit, because now there will be even more faint stars with even higher numbers. So at that point, it's kind of useful, though, to sort of deviate into just a little bit on stars, right? Because as the magnitude system began to kind of mature, it sort of became less qualitative and descriptive and more physically based. So you have to kind of come to this idea that not all stars are the same. They're not all intrinsically the same brightness, and they're not all intrinsically the same size. Of course, we kind of understand that this is the Hertzsprung-Russell diagram, which kind of summarizes stars, right? On this axis, you've got essentially what color they are, and on this axis, you got how bright they are. And all the stars kind of fall into their Sirius right there, the dog star, the one we were looking at. There's the sun right there. And this kind of tells us a couple things. First of all, it tells us that all stars are not equally bright, and all stars are not the same size. And they're not the same color either. So there's kind of physical issues with stars that kind of affect the visual interpretation of them. So we kind of have to start thinking about that a little bit when we start thinking about how the magnitude system has kind of evolved. Also, we have to kind of think about that third dimension a little bit, right? Anybody's ever looked at, like if you've ever looked at street lights, right? All street lights are roughly the same brightness. We'd like for them to be less bright, I think, because they fog up our sky. But you also know that if you look at one that's far away and you look at one that's closer, the one that's closer is going to be brighter and the one that's far away is going to be dimmer. You also probably realize, at least intuitively, that since they're both street lights, they're both intrinsically the same brightness. But if you didn't know that, it would be really hard to really say, is the difference due to intrinsic brightness or distance, right? So it becomes this kind of trade-off. From the magnitude perspective, as we're going to see, there is a solution to that, right? We talked about cosmic distance scales a little while back. I don't really want to go too much into that again. But the thing you got to kind of understand is that there's a regular relationship here. There's this thing called the inverse square law, right? And if you want to think about it this way, think about the source of light has a sphere of light coming out of it, right? And that sphere of light is what you see. And because it's a sphere, as it expands, it gets in the energy, in a sense, gets spread out over larger areas. So, there will be math, unfortunately. It's basically what it says is that the apparent brightness is equal to the actual brightness, the luminosity, how intrinsically bright it actually is, divided by the distance squared times 4 pi, because 4 pi is the surface of a sphere, right? So what this tells you, as you get further and further away from the source gets apparently dimmer really fast because it's happening as the square of the distance, right? So you square a number, you get a bigger number, right? So that actually leads to a couple of kind of important definitions for physically understanding magnitude. The first of them is luminosity. Luminosity is just the total amount of energy that's emitted by anything, really, but in this case we'll think of it as a star, per second, right? So the unit of luminosity is watts. A watt is a joule per second, right? It's a power per time. Actually, no, it wouldn't be power per time. Anyway, but that's the unit. That's luminosity. That's the intrinsic brightness of the star or other object. The apparent brightness then is how bright the star appears to be, and it's a function of distance as well. So it's given, it's the power per square meter emitted by the star at some distance, right? So apparent brightness is what's most closely related to the types of apparent magnitude that people like Hipparchus would have been looking at, right? They didn't realize, and Ptolemy and others, Galileo, they didn't realize that there may be intrinsic differences. So they were thinking of the brightness, the magnitude, only in terms of what was visible. So what they were doing was pretty close to apparent brightness, right? So again, just to kind of make the point here, if you know, apparent brightness doesn't really tell you, it tells you, it's what you perceive, or is what is perceived from Earth. Doesn't really tell us whether something is intrinsically brighter or further away. It just tells us how apparently bright it is. So that's what apparent brightness is. This actually matters because as astronomy developed, astronomers became much more interested in being able to actually measure brightness, not just estimate it, but measure it. And this goes back, this was a big surprise to me, is that it goes back a lot further in time than I would normally have thought. You know, I kind of thought about, we started measuring brightness of stars when photographic plates came along, right? Turns out it was much, much earlier than that. One of the first people to do it was Sir William Herschel, right? Herschel was kind of famous for building telescopes, and actually was a musician by trade, but an astronomer by avocation. And he was also a very inventive mind. There's his sister Carolyn, by the way, who we will talk about next time. Anyway, one of the things that Herschel was interested in was measuring light, measuring radiation. By the way, he was the first person ever to measure infrared light, and he did it with thermometers as well, which is a different story, but anyway. So he invented this device that was basically a visual photometer, and he was able to actually use it along with his telescopes. What the visual photometer actually did was project a light of a known brightness into the field of view, and then he could visually compare them. And he kind of was, from there, able to estimate brightnesses a little bit more quantitatively, and also fill in the scale a little bit. So he would talk about things being maybe a magnitude of 6.5, right? Or some other fractional number. So he was doing this stuff, I believe, in the 1700s. This goes back quite a ways. Of course, that led to some additional problems, because now we had objects that were being measured that turned out to be brighter or dimmer than originally thought. And so we needed a way to kind of relate, a way was needed to kind of relate that apparent magnitude to the intensity of, in other words, I guess maybe a better way to say it was a scale was needed, right? Not just a sort of categorical series of jumps, but an actual scale was needed. And so the person that kind of did that was this guy, Norman Pogson, was a British astronomer, and he basically standardized the scale. So what Pogson did was there were 5 visual magnitudes. He worked only with visual magnitude stars, right? There were 5 visual magnitudes, and what Pogson learned from doing some of this photometry type of stuff was that in this scale, a 6th magnitude star was 100 times dimmer than a 1st magnitude star. So 5 levels, 100 units. So he basically took the 5th root of 100, and that's about 2.51 something, and said that's the increment between magnitudes. So if you ever wondered why, you know, a 2nd magnitude star is 2.5 times dimmer than a 1st, and so on, it's because of that. And that number is called the Pogson ratio, and it's still in use. So each magnitude is 2.5, actually a little bit more than 2.5, dimmer than the preceding one. And this is the more quantitative relationship between those two things right there, but again, there's that Pogson ratio right there. So the other thing that Pogson needed was a was a sort of an anchor for his scale, and he chose Polaris to be the anchor, prominent star, right, the North Star. And so he used it, and he designated it as a second magnitude star. What's the problem with that?
Polaris is a variable.
Polaris is a variable star. Right, so it kind of turned out to be not a particularly good choice. It's still roughly a second magnitude star, but it varies a little bit. So that was fixed by picking another star, which we'll get to here in just a second, to be the anchor. Anyway, and so this, as the ability to actually measure the brightness of stars developed, right? Dimmer and dimmer stars could be measured, but they could be measured with more quantitative accuracy. So visual photometry kind of gave way to photometry from photographs, from astronomical photographs, right? Astronomical photography started in about 1840. That was not that long after Herschel was doing his work, which I believe was in the 1830s. So here's an old picture. There's the camera right there. Photos in those days were taken on glass plates, transparent glass plates, right? Which turned out to be a really good choice because they last. So there are photograph archives that are 150 years old that are still, they haven't stretched or warped or bent because they're on glass, and glass is rigid. But it was also transparent, so you could shine light through it. And if you could measure how much light shined through, you could measure the brightness of stars, right? So photography became a way of measuring magnitudes, and that gave way after a surprisingly short amount of time to measuring them electronically. So this was the very first photometry. Photometry is a word that just means measure light, right? Very first photometry was done in 1907. It was done by a guy named Joel Stebbins. He was working at that time at the University of Illinois. And when I was a graduate student at the University of Illinois back in the 80s, the building where my office was in was right next door to the observatory where he did this work. So, you could go over and actually see the telescope that, I don't know if they kept his apparatus, maybe the physics department kind of kept it as a, museum piece or something. But here's his apparatus right here, and he was using, you can see it's kind of scary looking, right? It's a lot easier to do this now. Back in those days, you could actually get physically killed doing this because they used capacitors and electronics to kind of charge up these things, and if you didn't handle them properly, they could zap you into next week. So you had to be a little cautious. They had to be brave in those days to be a photometrist. It's gotten a little better since then. Here's more modern photometers now. You can buy a very good camera for photometry now for $1,000, maybe a little bit less. So the ability to do photometry has improved remarkably, and so has the ability to measure the brightness of stars. So all that led to some problems. One of them was that they discovered that Polaris was a very, it's not only just a variable star, it's really variable. I don't know if you ever watch it, but I kind of look at it whenever I can, and I can see visual changes in its brightness through time. It's very noticeable. Anyway, so it's decided that they were going to go with a different star as the 0 point. So the new one that was selected was Vega, which was a 0 magnitude star and was thought to be stable. It wasn't. It's not a variable star in the same sense that Polaris is, but it is a star that in its visual magnitude stays roughly constant, but its infrared magnitude changes a lot. It's thought it has this disk of stuff around it, basically, that affects its infrared response. So it's now listed as having a magnitude of like minus 0.03 or something like that now. So it's still pretty close to 0, and everybody still calls it the 0 star, but it's technically not. But it's now the it was the second choice for kind of anchoring the system, basically, what you compared everything else to, right? It's also got some exoplanets around it. There's one of them right there. So anyway. Okay, so now it's possible to measure brightness much more accurately. That kind of also created a bit of a problem because of the whole distance issue, right? If you wanted to go from an apparent magnitude, right, just what it looks like, to what the brightness actually is, you have to take distance into account, and you have to standardize the distance somehow. So the system that was come up with here is called the absolute magnitude system, and it's actually pretty simple. All the absolute magnitudes you'll see, if you get a catalog of stars, look at the absolute magnitudes, what those are the magnitude of the star as it would appear if it was 10 parsecs away, right? 32.6 light years away. Why 10 parsecs was chosen, I don't really know. Anybody know that? I'm not sure exactly why that was the case,
I
but
think it was a drinking game.
drinking game. Maybe they just figured it was like a nice round number, you know? There's a surprising number of instances where that's exactly what happens. Like, oh, how about 10? But anyway, so for stars, the absolute magnitude that you'll see is what its brightness would be if it were 10 parsecs away from us, 32.6 light years. You can relate the apparent to the absolute magnitude. Again, there's more math, right? Damn that math. This is how you relate the absolute magnitude to the apparent magnitude. Little m is apparent, big M is absolute, or is it the other way around? Anyway, this is the reason why sometimes there are negative values now, because there's this subtraction in there. So it was found there were objects are actually brighter than Vega, right? So they go into the negative end of the scale. So this is the reason why d is the distance divided by 10. So if something is 10 parsecs away, right, this is going to be 1, right? So this whole term is going to drop out, and it's just going to be the same, right? Little m will equal big M. So that's how you relate apparent to absolute magnitude. Mostly you don't actually have to do this, though, because there's catalogs and stuff that tell us this. So here's some examples of stars that, with the absolute and apparent magnitudes included, right? There's Sirius right there. Apparent magnitude, minus 1.4. Absolute magnitude, plus 1.4. Kind of an interesting coincidence. But notice it's really not all that bright compared to, say, Alpha Centauri, right? Which is a much brighter star, but apparently dimmer. And there's another good example here. Spiga, brighter star, looks dimmer, right? So kind of get that sense of the interplay between distance and brightness. And so here's what, again, we looked at the dog, so here we're looking at the big dog again. Here's what the big dog kind of looks like with apparent magnitudes, right? The size of these circles here represent the apparent magnitude. They're Sirius, the big bright star, right? Here's what they would look like if they're absolute magnitude. Sirius, and then all of a sudden, not all that impressive, right? Much, much brighter stars, including some that look really small in terms of, or really dim in terms of apparent magnitude. All right, so we talked a little bit about the problems with Hipparchus a little bit earlier, right? It's qualitative. Well, we kind of, photometry and photography and Norman Pogson kind of put us on a little bit more firm footing there, right? Fixed high end, no, it doesn't. We now have any number we want, right? We're not limited to 6. Assumes all stars are intrinsically the same brightness. And the interplay of absolute and apparent magnitude kind of deals with that. Of course, you have to be able to measure the distance, but that's a topic for another time, right? We still have this problem, though. It's based on visual observation and that human color vision. And it turns out that not only is human color vision sort of a little bit limited, but sensor response kind of is too. So these curves right here sort of represent the spectral sensitivity of various sensors, right? This one right here is the human eye, and probably no surprise, mostly sensitive in the visible part of the spectrum. It's kind of a evolutionary trait, right? We evolved to see visual light because there's so much of it in our environment, right? But if you look at some of the sensors that we use, right, the human eye tends to peak in sensitivity around green or yellow, not so good at seeing some other colors. Some of these other sensors you can see, they peak in various other parts, and that actually can be a little bit of an issue when you're trying to measure the magnitudes of objects that have kind of different colors, right? But you can also kind of think of the problem backwards as well. So there's the absolute magnitude of a star, but then there's also its color magnitudes, how bright it would look if you only looked at it in particular colors. This is actually the basis for a lot of photometry systems. We have color filters, color brightness filters for the
It's
Tombow,
on,
right?
it's on the scope, and they're photometric filters.
And they're the UBVRI set. Yeah. So
The BVR, I think we didn't go
We didn't
into.
get to use it. yeah. So when you see magnitudes of stars sometimes, and this would be in a little bit more of a technical presentation of their magnitude, you might see several numbers in different parts of the spectrum, right? So this is the B filter, which is kind of bluish, I guess, and the visual filter, which is really more yellow.
Yeah,
And
it's
so-
kind of yellow-green.
Yeah, and so on. And so photometrists often measure the brightness of stars in lots of different wavelengths, and that becomes very important physical information about the star. So there's Alpha Canis Major, right? That's Sirius, and this is its various magnitudes. So its U magnitude is minus 1.5, and it's actually fairly uniform across all of these UBVRI, and then J, H, and K, which are even longer wavelengths further out in the infrared. So you can kind of see that its magnitude doesn't really vary an awful lot, but it's basically a little bit dimmer in the longer wavelengths. And this is actually sometimes really important physical information. So one of the things that a lot of amateur astronomers do is they measure the light from stars in these wavelengths, and that becomes very important physical information for kind of understanding them.
What makes that tricky too is when you're measuring something that's overhead, that's a red star, it survives going through the atmosphere better than a blue star does. A blue star gets knocked out very quickly because of the atmosphere. So it changes its magnitude over a brief area of sky, whereas a red star holds on longer.
And interstellar dust will do something similar, but the other thing about the atmosphere is if you're looking at an object that's straight overhead, right, you're looking through less atmosphere than if you're looking at something closer to the zenith. So you can get apparent changes in spectral brightness by angle, right? So it's what makes all this tricky, which is, why they pay those astronomers so much money to do this sort of thing. It's a difficult job.
Why we make so much money?
That's right. That's why we make the big bucks. But anyway, so this is just kind of another way of kind of thinking about magnitude. Well, that's talked a lot about stars. What about extended objects? They're usually listed as having magnitudes as well, right? And in the case of extended objects, things like galaxies and nebula, the absolute magnitude of them is still figured the same way. It's scaled to 10 parsecs. But the way the magnitudes are actually estimated is you basically sort of average across the object. With something like a galaxy, right, there's a lot of variation in brightness across it. And you can actually measure the magnitudes in some cases of individual stars or objects that are inside the galaxies. But if you see a galaxy magnitude quoted, it's going to be average across all of it. With something like a nebula, kind of the same idea, but again, these things are closer to us. They're in our solar system, they're in our galaxy, and they've got objects embedded in them, which kind of complicates things a little bit, but that's essentially how you handle extended objects. Solar system objects are a little bit of a different story for a couple of reasons. First of all, they're not 10 parsecs. It's ridiculous to think of them as being 10 parsecs away, right? Because they're in our solar system. Secondly, their angle relative to us changes pretty rapidly, right? Things that are far out in space, they're moving, but they're moving at a relative speed that's pretty slow, right? So there's the angular displacement.
Apparent speed is extremely slow.
Yeah, but stuff that's close, that's not the case. In some cases, things are booking along pretty fast, right? These guys that measure NEOs can probably tell you all about that. So it means you have to kind of think about what the magnitude of it is in a little bit different way. So as far as how you can conceptualize the distance, magnitudes of solar system objects are scaled to the sun, right? So it would be the magnitude relative to the distance to the sun. Right? That's the scaling there. But you also have to kind of think about their angle. So this is all a bunch of, I guess I went a little overboard with the math tonight. But what this is basically telling us is that you know, if you're the observer and you're observing something, there's an angle between you called the phase angle, right? And if, as this observing position changes, that phase angle changes, and the apparent brightness of the object might also change just because the light reflects off it in a different way, right? Or the angular reflectance of it comes into play. So in a lot of cases, this is kind of finessed by trying to measure the magnitudes of things when they're at opposition, right, directly across from the sun. But you can't always do that.
When you think about it in terms of the moon, if the moon's full and it's directly opposite the sun,
It's
it's
gonna be-
at its brightest. But if it's a quarter moon, which is, you know, the 90 degree away,
Yeah.
then it's half there or smaller
Half or less, yeah.
amount of brightness.
Yeah. So if you really want to calculate that phase angle, it follows from something you probably learned in trigonometry, the law of cosines, right? And then this is how you kind of relate those two things to each other. But it is a little bit of a different thing. So what do we get? What are the typical neo magnitudes?
It depends, but the fast ones that are moving very quickly are generally 15.
15. I've seen
Somewhere around
some of them
there.
are as low as like minus 19 or so, aren't
Well, they can get that way, but it's, I mean, you mean absolute magnitude
Yeah.
or apparent?
Apparent.
Apparent magnitude, they can go down to, you know, brighter than most stars, so,
Yeah.
yeah, just how close they are really matters.
Yeah. As far as what all this might mean then for observation, here's a little rough scale that I found. I couldn't find a really good one of these, which was a little disappointing. But the sun is about minus 26 magnitude, super bright, right? You know, don't look at it. Full moon about minus 12, I would say. Again, as the phase.
Seems like minus 20, but yeah.
Yeah, sometimes it seems like even worse than that, right? Venus is a little bit, at its brightest, about minus 5. Jupiter and Mars, maybe minus 3. But again, varying quite a bit depending on the time of day, you know, where it is in its orbit. And also the distances change, right? Saw that Vega was the 0 star. Alpha Centauri is actually a pretty good 0 star as well. There's Polaris, it's still about 2, but it's a variable star. So as far as what you can actually see with various bits of equipment, the human eye is still considered to be about 6 magnitude, faintest object to the unaided eye. And again, that sort of depends, number one, on having very clear skies, right, dark skies, and having good eyesight, which mine, unfortunately, is not what it once was. I don't know if I could pick up a 6 magnitude star with my eyes anymore. Might be worth trying it. 1 meter telescope, you'll get you down to about 18 or 19.
That's wrong.
You think that's wrong? Because you get that, you guys get that out at Farpoint, right?
Visually,
With your eye.
he's talking visually.
Yeah. Yeah, this would be observational if you
Oh.
looked through it. If you put a sensor on it, like
Oh, yeah,
a
you go way up.
CMOS sensor or something like that, then it would probably be,
Minus 23 is what
Yeah.
we can theoretically get to.
and that's
Okay.
that's with about a 0.75 meter telescope,
Yeah,
0.7,
point 7,
and dark and
relatively. dark.
relatively dark skies.
Yeah.
So and a CMOS camera.
Yes.
Right, so that's what the club's
Even the
equipment.
old CCDs would do that eventually.
Yeah. The 4 meter telescope with Kit Peaks has a 4 meter telescope, ground based. If you were to look through it, which you never would be able to do because nobody would want to spend time doing that.
That may all.
Yeah, 26 maybe, and so on. I don't know why they put the Hubble and Keck on here, or why they put the Hubble in here, because nobody ever looks through it, right? But
Well, not for very long.
no. It'd be a fun experience while it lasted, but it wouldn't last very long. Anyway, so this just kind of gives you some idea. I think a pair of binoculars would get you about 10th magnitude, wouldn't it? Good pair of binoculars. Anyway, of course, the one thing that we always have to kind of bear in mind is this is under relatively ideal conditions. And as we unfortunately know all too well, sky is getting brighter and brighter, right? So we haven't really talked too much about the brightness scale, but I think Farpoint's about Bortle 3, right? maybe
It's
borderline
kind of
3, 4
borderline now
now.
between Border 3 and Border 4.
I think I've been in Bortle 1 one time, and it was so dark, it was almost frightening.
Yeah.
But, you know, you literally couldn't see your hand. I mean, literally could not see your hand in front of your face. So anyway, that does kind of interrupt this. But anyway, so that's it. A little bit of background on the magnitude scale. Hopefully that'll kind of fill in any gaps. I learned a bunch of stuff, including that, you know, photometry is much older than I thought, and Norman Pogson was the guy that came up with that number. So it's always a good experience when I learn something. Questions? Okay. Well, thanks for coming. Next month, we'll talk about Carolyn and Carolyn and telescopes.
Anybody think of any topics they're interested in, since we have a pretty good crowd and had time to think about
A
it?
few minutes.
I did hear that the JWST has picked up some objects that were outside of the sphere of the observable